Ayubowan students, and welcome to Study Hub Sri Lanka. It's great to have you with us for another A-level physics lesson.
Today, we're diving into a really fascinating property of liquids, something you see in action every single day, probably without even realizing it. We're talking about surface tension.
Have you ever stopped and wondered how a tiny insect can just walk on water like it's solid ground? Or why a water droplet holds that perfect, beautiful spherical shape just before it falls from a tap? Well, the answer to both of those questions is exactly what we're talking about today: surface tension.
So, here's our game plan for this explainer. First, we'll figure out what surface tension actually is. Then, we'll get into the molecular reasons behind it. We'll look at some key forces called cohesion and adhesion, see how that leads to liquids climbing up tubes, then we'll crunch some numbers with energy and work done, and finally, we'll figure out the physics of a soap bubble.
Okay, so let's start with a big picture. What is this phenomenon that we can actually see and observe all around us?
The easiest way to think about surface tension is with this simple idea. Just imagine that the very top layer of any liquid, it's acting like a thin, stretched-out rubber sheet, a kind of elastic skin. It's this skin that's strong enough to support an insect or even a carefully placed steel needle.
But of course, there isn't really a skin on the water, right? So why does it act like there is one? Well, to understand that, we need to dive deep down to the molecular level and look at the forces between the molecules themselves.
Okay, take a look at this diagram. See molecule A, it's deep inside the liquid. It's being pulled equally in every single direction by all of its neighbors. The forces are balanced. But now, look at molecules B and C. They're on the surface. They don't have any molecules above them pulling up, right? So the result is a net, unbalanced pull downwards back into the liquid.
And that, right there, is the crucial point. Every single molecule on the surface is being pulled inwards. This massive collective pull makes the surface try to shrink itself into the smallest possible area. And that action creates the tension we observe. It's almost like thousands of tiny invisible hands pulling the surface tight like a drum.
Now, this tension is all about intermolecular forces, and there are two main types you really need to get your head around: cohesion and adhesion. These two forces basically decide how a liquid is going to behave when it comes into contact with a solid surface.
It's pretty simple when you break it down. Cohesive forces are the attraction between molecules that are the same. Think of it as water molecules sticking to other water molecules. Adhesive forces, on the other hand, are the attraction between molecules that are different, like water molecules sticking to the side of a glass.
So, let's see this in action. If you put a drop of water onto a clean piece of glass, the adhesive forces, that is, the attraction between the water and the glass, are stronger than the cohesive forces holding the water drop together. And what's the result? The water spreads out and wets the surface of the glass.
Now check this out. It's the complete opposite with mercury. Here, the cohesive forces, the attraction between the mercury atoms themselves, are way stronger than the adhesive forces to the glass. So instead of spreading out, the mercury pulls itself into a tight little bead, trying to minimize its contact with that glass surface. And we can actually measure this battle between the forces using something called the angle of contact, which we represent with the Greek letter theta. For water on glass, where adhesion wins, you get an acute angle, less than 90 degrees. For mercury, where cohesion wins, you get an obtuse angle, more than 90 degrees. So this angle is a great indicator of which force is stronger.
Okay, so now that we've got a handle on this tug-of-war between adhesion and cohesion, let's see how it leads to another really amazing effect called capillarity. This is what happens when liquids get into very narrow spaces.
So if you take a super thin tube, what we call a capillary tube, and you dip it into a liquid, one of two things will happen. As you can see in Figure A, some liquids, like water, will actually climb up the inside of the tube, defying gravity. But for others, like mercury in Figure B, the liquid level inside the tube will actually be pushed down.
And the reason for this comes right back to what we just learned, the angle of contact. It's that simple. If the liquid wets the glass, meaning it has an acute angle, the strong adhesion will literally pull the liquid up the walls of the tube. But if the liquid doesn't wet the glass, if it has an obtuse angle, then the strong cohesion will cause the liquid to pull itself away from the walls, causing the level to fall.
All right, everyone, pencils ready? This next part is really important for your exams. Let's start putting some numbers and formulas to these ideas. How do we actually calculate surface tension and the work done against it? So, the formal physics definition:
We defined surface tension, which we represent with a capital T, as the force acting per unit length on the surface. So the formula is T equals F over L, and its units are newtons per meter. This is a really key formula you're going to want to remember.
Now, let's use that to figure out the work done when you stretch a soap film. Here's the one thing you absolutely must remember. A soap film has two surfaces, an inside one and an outside one. That's why the force isn't just T times L, it's T times 2L. Then, we know work done is just force times distance. So if we substitute our force in, we see that the work done is simply the surface tension, T, multiplied by the total increase in the surface area.
All right, for our final section, let's apply everything we've learned to something we all know, a simple soap bubble. Why are they always spherical? Well, it all comes down to a perfect balance of pressure.
Think back to that stretched elastic skin idea. The surface tension of the bubble is constantly trying to collapse it, always pulling inwards. So, to stop the bubble from collapsing in on itself, the air pressure inside the bubble has to be just a little bit higher than the air pressure outside. This extra, or excess pressure, pushes outwards, creating a perfect balance with that inward pull of tension.
And of course, we have a formula for this excess pressure, P. It's P equals 4T divided by R. Here, T is our good friend surface tension, and R is the radius of the bubble. Now, take a close look at that 4. Why is it 4T? Because, just like our soap film, a bubble has two surfaces, an inner one and an outer one. For a simple liquid drop in the air, which only has one surface, the formula would be 2T over R. So don't get those mixed up.
So let me leave you with a final thought to really tie all these ideas together. Looking at that formula, you can see that the excess pressure is inversely proportional to the radius, meaning the smaller the bubble, the higher the pressure. So can you use that to explain why small bubbles are almost perfectly spherical, but really large ones get distorted and wobbly? Think about it.
And that's our deep dive into surface tension. I really hope this has been a clear and helpful lesson for you. Thank you so much for joining us here at Study Hub Sri Lanka, and we will see you again for the next Physics Explainer. And please, before you go, don't forget to subscribe to our channel, Study Hub Sri Lanka, and make sure you click that little bell icon. If you do that, you'll get an update immediately whenever we post a new lesson for you. Keep up the great work with your studies, and I'll see you in the next one.